Now let's consider the forces due to what we call buoyancy on submerged bodies. So for instance, if I have this chunk of stuff that's underneath the surface of the water and the top of it at any given location is some distance ht under the water. And of course ht is going to be different for everywhere on the surface. And likewise I could talk about the distance down to the bottom, hb, and that'll be different for every point on the bottom surface here. And I could also think about the thickness of that body in the vertical direction as somehow describing its shape. And again, the thickness will vary depending on how we move back and forth in the XY plane. So there's our vertical upward Z, X, and Y. And this plan form, this horizontal XY plane, is the plane that we're going to have to think about integrating over. Because once again, the horizontal components cancel. If I look at the pressure forces acting on the outside of this body, they act normal to the surface all the way around. The pressure is higher on the bottom than it is on the top. And the net result is that we'll have a net upwards pressure force because these pressures on the top are smaller in average than the pressures on the bottom. So as a result, we'll have a net pressure force, and that pressure force is what we refer to as buoyancy. So buoyancy is not magic. It is just equal to the sum total effects of the pressure forces due to the varying pressure in elevation. So if we've taken into account those pressure forces on the outside surfaces, we don't need to then again add in buoyancy. So the horizontal components will cancel out. For every pressure force on this side acting over a projected area in the XZ plane, there's a force over on this side of the same magnitude acting over the same area in the opposite direction. So the horizontal components of these buoyancy forces are going to cancel out. That means we need to look at the vertical components. Well, if I look at this pressure down here, for example, the vertical component of that pressure force down here is larger than the vertical component of this pressure force up here. So on this little chunk of the body here, the pressure force acting on the bottom is bigger than the pressure force acting on the top. And the result is we're going to get a vertical force that is net positive. That is, it's a force that's going upwards in the positive Z direction, and that's because the pressure is higher on the bottom. So let's look at our thickness as a function of position. That thickness will be a function of X and Y. That defines the shape. And we can get our buoyancy force, which is just going to be the force resulting from the pressures, by integrating over the area, the projected area in the XY plane, on the bottom, rho g times h on the bottom, that's the pressure on the bottom here, times dA. That'll be the upward force from all over the area that's on the bottom, all of the area that's facing downwards. And we'll have to take into account that chunk as part of that area, and all of this stuff that's right down here on the bottom, and integrate over that entire space. So we're going to need to know a fair bit about the shape. Now, then we're going to have some forces acting on the top. They're going to be acting downwards, so it's going to be negative integral over the area, rho g ht, how far the top is below the surface of the water, times dA. So if we do our accounting carefully and make sure that we get all of the area and only the appropriate thicknesses associated with that area, so we'll have two separate little chunks over here where we've got this concave bit on the side, then our integral will work out. We'll be calculating all the pressure forces all the way around, and we can combine that by noting that the thickness is the difference between the height at the top and the height at the bottom. So that F, buoyancy, is going to be the integral over the area of rho g times, well, everything's the same in these two except it's the height down to the bottom minus the height down to the top. Or if we remember that we've got the thickness there, then that's going to be still an integral over the area of rho g times the thickness times dA, but thickness times projected area is a volume. That'll be the integral over the volume, triple integral, rho g dV, which brings us back to the weight of the displaced volume. So buoyancy, it's just a result of pressure forces acting on the outside, but it turns out that, as Archimedes tells us, it's always going to be equal to the weight of the displaced volume. We're going to need to make sure that this density we're using here is the density of the fluid, not the chunk of whatever it is that we've got under the water. In fact, the density of this block doesn't matter at all to the buoyancy force. It is going to matter to the force due to gravity that's exerted because of the mass that's within this body. So if the mass of this body is smaller than the buoyancy force, it will tend to move up to the surface. If it's heavier than the buoyancy force, it will tend to sink. And if it's exactly equal to the buoyancy force, it'll just hang there in the water at that level. So we can always go back to Archimedes, and we can always get the complete buoyancy force, the total overall buoyancy force, by taking the weight of the displaced volume. However, we can better understand what's going on if we think of buoyancy as a distributed pressure force distributed over the entire surface of the body. And that will show up in the next couple of segments as we talk about the stability of things that are floating in the water.